Hey everyone, my name is Reagan Brumme, and for my interactive case study 5, this is going to be my take on this presentation, and I'm going to try and walk you through everything and also make it relatable because this topic can be kind of hard to understand, and the way I'm going to be explaining it, I hope it can help you all understand better. So I'm going to be talking about GABA, which is the neurotransmitter that basically keeps your brain from, I'm going to say, acting like a group chat whenever your notifications are turned on. When your GABA levels are too low, neurons talk over each other, and that chaos can turn into seizures. So today I'm going to be showing you how Vigabatrin boosts the brain's natural quiet signals, and also show from the UCSF Chimera program the actual structure where the drug binds. So once I show the 3D structure, the mechanism will make sense, and I hope this presentation helps. Here we go. For my first slide, it is titled How GABA Works. So this slide is the scientific version of my group project analogy I'm going to be using. So when GABA binds to its receptor, it opens these chloride channels, which in the image I chose, it's the yellow structures. Chloride is going to flow into the neuron, and it makes the inside more negative, and that is the quote-unquote do not disturb mode that I mentioned. By polarizing the cell, GABA shuts down unnecessary action potentials and keeps glutamate, which is the overstimulated team member, from taking over. And the two pathways listed here, GABA A fast and GABA B slow, are just the two speeds of GABA that the brain uses to keep calm and organized. Now moving on to my next slide on what a seizure actually looks like. So the diagram I chose for this slide shows how a seizure spreads. On the left, the EEG is normal, but in the middle, you see the big spike. That is where one neuron starts the quote-unquote stadium wave. The inhibitory signal, which GABA should control, but when it's too weak or delayed, that's when we can see the intracellular traces underneath. This is because inhibition can't stop the excitement. The activity spreads through the network and turns into the hyperosynchronous burst on the right, which is the full seizure. And that's important here to understand because this doesn't just happen from too much excitation. It also happens when there's not enough inhibition. That's why drugs like Vigabatrin boost GABA and strengthen inhibition, and this stops the wave before it takes over. After being able to understand what a seizure looks like using the diagram, we're going to be also talking about how Vigabatrin actually works. So for this, my diagram basically shows exactly what Vigabatrin is doing. On the left, the purple over is the GABA transaminase, which is the enzyme that basically cleans GABA out of the system. Vigabatrin, which is the green box, slides right into the enzyme and shuts it down for good. Once that happens, GABA doesn't get broken down anymore. You can see all those extra purple dots building up in the presynaptic terminal and then drifting into the synapse. That means that more GABA actually reaches the GABA A receptors at the bottom, which strengthens inhibition. So I'm going to use a analogy about like cleaning your room. So imagine GABA T is a person making the mess, and Vigabatrin is like locking the door so they can't come back in and make a bigger mess. So it's not sedating the brain, it's kind of just letting GABA do its job the way it's supposed to. So now, after being able to understand this, we can use the Chimera visualization, and when I open the 1-OHW structure, you can see the whole GABA transaminase enzyme, and right in the middle of those coils is the active site. And when I zoomed in, which is the bottom image, it lets you actually spot Vigabatrin, and it's a cluster of colored sticks. And this tiny connection right here is the covalent bond between Vigabatrin and the PLP factor, which is the definition of suicide inhibition. Seeing it in Chimera makes it look much cleaner though. It's like catching the enzyme right at the site where it permanently get shut down. So understanding this and being able to see this in UCSF makes this a lot easier to connect and us to be able to understand the Vigabatrin mechanism. Now that we've went over the main idea and what it looks like and what it does and how it does it, we're gonna correlate Vigabatrin mechanisms to real life. So my image is showing the real life implications. So the confusion, twitching, falls, staring spells, all these symptoms come from the same problem we saw earlier, which is the brain losing its inhibitory control and slipping into the overactive firing pattern that happens. So Vigabatrin directly targets the source of that imbalance by blocking GABA transaminase and boosting natural GABA levels. It helps stabilize these circuits and prevents many of the complications shown here in my image. So that tiny covalent bonds we saw in the chimera visualization isn't just a molecular detail, it's also what allows patients to have fewer seizures as well as a safer, more stable quality of life. In conclusion, I hope everybody enjoyed my presentation and is now able to understand GABA and what it does and how the seizures occur when it breaks down, as well as the Vigabatrin, which blocks the GABA transminase at its source. I hope everybody enjoyed this and can understand how we can relate this also to real life scenarios and real patients and how this can affect people and improve their quality of life. Thank you.